My name is Douwe Geuzebroek, LioniX International, and I will discuss about narrow linewidth tunable lasers based on a hybrid assembled photonic integrated circuit technology. And let me this work. Yes. So a bit about LioniX International. We provide customized microsystem solutions, which means that we do photonic integrated circuit, but also customized MEMS. And we design that for our customers. We don't have our own product. It's always something that we design for our customers there. And we take a vertical integration approach to that. So we can do the design up to the device there. So we do the design, we do the manufacturing of the photonic integrated circuit, but also spend a lot of time and effort on assembling and packaging this. And we can do that in scalable production volumes, scalable both in the sense of we want to grow with our customers from a prototype up to given volumes, but also scaling in different kind of volumes. Telecommunication market, of course, has a high number of it, but many of our customers, because of our silicon nitride technology, can deal with 100 or 1,000 pieces a year, and that's also fine. And we should also be able to support that. We started out in 2001, and we have always been at the forefront of the silicon nitride waveguide technology, and we keep doing that, providing a strong IP position there, supporting many developments in universities and in research projects. So our core technology is called triplex. Triplex is based on silicon nitride waveguide technology. It is called triplex. Triplex is the Dutch word for plywood. So it's built out of multiple layers of silicon nitride. So it's a single waveguide built out of multiple layers. We do that because we can then control the properties of the waveguide quite well. We have a very low loss optical waveguide in the order of 0.1 dB per centimeter for the high confinement ones, and the 0.1 dB per meter for the low confinement ones. We can adjust the polarization properties for polarization independence or optimize for one of them. And it's a very broad band. So it's not only the telecom window which is of interest, but we can go as low as the visible, the blue wavelengths, and as high as 2350 nanometers. Can have a small band radius there, and because of this multiple silicon nitride layers, we can quite easily make spot size converters, and we can do both processing on glass as well as in silicon. So for this tapering, that's one of the tricks, and one of our core technologies there is that we can taper down from this high contrast double stripe waveguide down to the single stripe low confined waveguide. You expand the mode and you have a very good coupling towards your fiber, or to any other material, and that's what this talk is about, coupling it to indium phosphide gain sections. We can control the mode of our waveguides very well. So the nice thing about silicon nitride is that we have low loss and you have a broad wavelength range, but the less nice thing is that it's a passive material. We cannot generate lights, and we do not have any electro-optic modulating speeds or so. That's why we are a strong believer in hybrid assembly. So attach indium phosphide or any other semiconductor material against the silicon nitride waveguide materials there to gain the best of both worlds there. It's something that we have done a lot, and we have a development going on there coming from the microwave photonic area, where you need to have high frequency signals transferred over an optical carrier to be processed in the optical domain. So that's an example of that is given here, where you see the silicon nitride chip, which is the big one over here, if you can see my pointer. And and it is placed, go back, yes. And it is placed next to the indium phosphide gain section there, and together it is a radio frequency in, radio frequency out optical link using hybrid integration to with a reduced radio frequency crosstalk there. So it's basically built out of a tunable laser, an external cavity tunable laser on chip, application-specific functionalities in the sense of an optical beamforming network, splitters and filters all in silicon nitride, but the gain section, the modulators, and the detectors are based on indium phosphide. Why do we want to do this? The gain link of this such a link that the optical power is of importance, and by doing this we can create very high optical powers, as I will discuss further. So laser basics, right? A laser are two mirrors and a material in between which has a gain of the optical signal. And the way that we implement that is one of the mirrors we implement on the silicon nitride using a reflector based on microring resonators. Can be either a single ring reflector or this double ring reflector at the bottom here. If you have the double ring reflector, you can use a Vernier effect. So having two rings with different radius, you can have a larger free spectral range there. And if you combine that with a gain bandwidth of an indium phosphide gain section, for example, you can create a laser which lasers only on at one frequency there. And but because these so in the double ring we now attach is a semiconductor optical amplifier. If you are hitting one ring, you can the spectrum hops because it hops back and forth between the free spectral range of the other ring there. But if you tune everything correctly, you can see it in these animations here. You can have a continuous sweep over the whole C-band in this case. So the bottom right animation is a measurement, not a simulation. You can completely tune it over the whole C-band and even further there. We have assembled it in several housings, including different kinds of butterflies. And the typical specifications of that are that we have output powers in the order of 10 milliwatts up to 50, line widths lower than a kilohertz, tuning around over the C-band and millisecond switching speeds. The side mode suppression ratio of more than 40 dB, and a mode hop free tuning range of about 0.2 nanometers. If we go a bit deeper then in the single gain laser, so that's where only one indium phosphide gain section is attached to it. If you bring it down to how far you can reach there, this is some work done at the University of Twente. And you see if you have very large ring. The nice thing of silicon nitride, because of the low losses, you can make a very long cavity length and long resonators there. And long resonators mean that you can have a very narrow line width. So in this case, a cavity was designed here, and the tuning it's given here. Sorry, it's a tuning of less than a kilohertz with a side mode suppression ratio of 60 dB, tuning over 18 nanometers of wavelength here. The University of Twente has shown that you can go as low as 40 hertz of this line width if you need that. Depending on the design, you can extend the tuning range there. So the maximum up to now is 120 nanometers of tuning. It all depends on the gain section and the design of the different microring resonators. The noise and the line width are comparable to what is available in the market there. It's got a very low intrinsic line width there, and that's and the RIN is as well as comparable to other systems. The nice thing about integrating it and a hybrid integration is that you can double things. So what if you apply two semiconductor chips to the chip, and the laser works as one? So in this case, this is one of the schematic there. So there are now 2 gain sections, 2 phase elements, this microring resonator, and they are combined to a single output. So the 2 gains act as a single laser. Its output power is controlled by a tunable coupler, and the output is coherently combined to one laser output. In this case, the highest output power was achieved by 80% coupling of the tunable couplers. That's a balance between the amount of laser light that you get out of your system and the amount that stays in to generate more photons. Right? Given a so quite linear behavior here, up to 100, even close to 120 milliwatts inside the chip, and it was all in single mode operation, side mode suppression ratios of 50 dB, and gain saturations begins over 300 milliamps. And we think that it was limited by the thermal conductivity that we had there. The RIN was again good, and mainly limited by our measurement system here. Same holds for the frequency noise. I think the white noise floor was we were measuring up to the white noise floor, and the 1/f square noise is mainly comes from the design of our electronics there. We could measure that the whole system, the whole silicon nitride system, has a 0.08 dB per centimeter losses, which that's why we can have this narrow alignments here. So some total numbers of the tuning range here, the output power, the laser output over the whole C-band and a bit more. As you can see, the output power is relatively flat, except for the part at the 1580 region, and the spectrum as seen at the reference port there, you can see the peak shifting. So it's a hybrid assembly where we connect an indium phosphide gain section to a silicon nitride chip. How stable is that? This application needs to fly in an airplane because it's a microwave photonic application for communication between an airplane and a satellite. So this goes vibration tests, and we went up to 40 gig root mean square, which was 10 times over the required level. And the assembly technology that we have there is can deal with this and can deal with these kinds of vibrations and shocks. A technology that we are improving there is what I have talked about now was a butt coupled, so a side coupled indium phosphide to a silicon nitride laser. We have done some work together with HHI to do it on a flip chip based, so an indium phosphide chip with some additional features on it, which is flip chipped in a hole that is etched on a silicon nitride platform. It also means that then one of the alignment tolerances, alignment directions can be done passively because of the vertical alignment stops there. So we only need to align in one direction then. So that's compatible for the wafer scale integration there. And for the first attempt, we had a 1.6 dB coupling loss, whereas normally we would be a bit closer below the 1 dB. So there's some room for optimization there, but we are quite happy with these results there. And we could have 60 milliwatts of power into the triplex chip. So on the photograph, it looks like this, where you have the different, either the different indium phosphide chips in different holes, or a indium phosphide array flip chipped into multiple holes at once. So this work was done together with HHI, and some references are given here. So what can you do with this? well, many things, and I think the nice thing why you want to use it of silicon nitride is that you can use other wavelengths as well. We have shown recently, together also with University of Twente, we have shown that it can also be transferred to visible wavelengths even, where we have shown a tunable laser in red, having a tuning range of 11 nanometers there. The nice thing about silicon nitride is that you can place, once you are integrating this laser, you have room for application-specific functions on the chip as well. So that's our driving design for the microwave photonics part of it, that the beamformer is in the silicon nitride there. So when you have this laser, you can have your application-specific functions added to it. And this component is now also offered in our multi-project wafer as a standard building block. So you can design your building block within our PDK. The silicon nitride part is then placed on the on your die, and in the assembly afterwards we connect an indium phosphide gain section to it. So also within the multi-project route, you can start working with a external cavity tunable laser as we have it available. So conclusions: we have shown excellent hybrid integrated lasers with sub-kilohertz line widths, output powers of more than 20 dBm for the single gain ones, and a broad tuning range, and stable and passing vibration testing. It's a low-cost route via the flip chip one as well, and other wavelengths are possible. As said, you can add application-specific functionality, and it is available as a building block in our MPW. So that gives me to the last slide to discuss any ideas.
Thank you very much for that very nice talk. Once again, I invite attendees to post any questions, preferably on the chat, although if you do post them on the Q&A, they will be, I think, repeated in the chat. I don't see any at the moment, so I'll ask my standard question, Douwe, about wideband tunable lasers. What kind of cost premium did you see for something capable of doing 120 nanometers versus a C-band 40 odd nanometer type of laser?
Yeah, so for us it is based on it's a different gain material there, so the cost is not too much effort there in relation to if we would make a standard C-band type, right? There are of course tunable lasers at this moment available, which already have a process which is much more optimized for cost. We are on the high side of the spectrum there, but that's something that goes down as also our volumes rise there.
Okay, thank you. I don't see any further questions, so I think we can thank you once more for a very nice talk.